Hello there, everyone, and welcome to this chemistry clinic for the LAE. We are live on YouTube. I am Dr. Owusu, and in this live session, I'm going to talk you through some of the theory underpinning acids and alkalis. We're also going to look at titration calculations and also try and get a stronger understanding of the practical aspects of acid-base chemistry and carrying out titrations. So this live session, which will be about 50 minutes long, will be split into three parts. We'll start by looking at the theory side first, so OCR AS chemistry theory on acids and alkalis. And then in the middle part, we will look at the practical aspects for doing titration, for doing titrations, and to look at the pieces of apparatus you would need and how to ensure that you can carry out titration accurately. And then in the final part, so the third part, we will be doing some titration calculations. I have picked a selection from a past exam paper, as well as some harder unstructured titration calculations. So hopefully you will leave after 50 minutes with a sense that you can go away and tackle some of the harder unstructured titration calculations. And then this should hopefully set you up for any assessments you've got coming up on the topic. Brilliant. So what we will do to start off with is look at some theory. And before we do that, I'm going to share my iPad screen with you, and then we'll hit our stride. So if you just bear with me for 1 second while I share my screen. Okay, so we're all set, and of course there's no better place to start than defining what acids and what alkalis are. And the OCRA syllabus sort of looks at acids in terms of their ability to release H+ ions or protons in aqueous solution. So any substance that releases H+ ions in solution, aqueous solution, is classed as an acid. You can also think of acids in terms of the Bronsted-Lowry definition, which your syllabus doesn't mention at AS, which is that it's a substance that donates a proton. Okay, so acids release H+ ions in aqueous solution, and as an example, we can have hydrogen chloride gas, for instance. If I write an equation to show exactly this, so we've got HCl gas, which you can bubble into water. So we can write AQ as shorthand for dissolving hydrogen chloride gas in water. And as a result of this, we end up forming aqueous H+ ions and also chloride ions. Okay, so this is a typical example of an acid dissolving in water to release protons, and we can certainly at AS you do need to learn the formulae of some of the common acids. So for example, HCl, which we've got in this equation. You'll also encounter sulfuric acid, which is H2SO4, and you'd also be required to know the formula of nitric acid. And these are all examples of strong acids. And as an example of a weak acid, we've got ethanoic acid, which is CH3C double bond OOH, or CH3COOH, as shown here. So these are all examples of acids that you're required to know at AS on the OCR course. Alkalis, on the other hand, release OH- ions or hydroxide ions in aqueous solution. And perhaps the most common alkali that you will have come across is sodium hydroxide. So if we look at an equation for sodium hydroxide comes in solid pellets, so sodium hydroxide pellets, and if we dissolve that in water, so AQ, you will end up forming sodium ions, aqueous sodium ions, as well as forming hydroxide ions. Okay, so along with sodium hydroxide, other alkali that you will come across at AS include potassium hydroxide, so KOH, and you will also come across ammonia, which is an alkali. Okay, so Definitions are incredibly important, obviously, and you may, in some instances, be asked to simply state the definition of an acid. It's also incredibly important that you're able to recognize acids in reactions, and also to be able to tell if the acid is reacting with an alkali and therefore taking part in a neutralization reaction. Okay, so we've seen some examples of strong acids and weak acids, and also some strong alkali and one weak alkali. But let's look at the distinction between these strong acids and weak acids. Okay, so on my screen, you should be able to see a definition for strong acids, and we're told here that they completely ionize or are completely dissociated in aqueous solution. So on the previous screen, you saw me describing how hydrogen chloride gas can be bubbled into water, and in so doing, your hydrogen chloride molecules completely ionize into H plus ions and chloride ions. So we can look at another example here. So if we've got sulfuric acid, and again, we dissolve this in water, you will find that you no longer have sulfuric acid molecules, but what you end up with are 2 moles of H plus ions, and these will be completely dissolved in water, so aqueous H plus ions, and you would have the sulfate anion, so SO4 2 minus, and that would also be in water. So H2SO4, which is a molecule, when dissolved in water, completely dissociates, completely ionizes. So there are no molecules of H2SO4 in the water. It's all H plus ions, so protons, and SO4 2 minus ions, aqueous. Okay, so strong acids completely ionize, completely dissociate in water. Now, what about weak acids then? So again, definition on the screen says only a small proportion of the acid is ionized in aqueous solution, or that it is partially dissociated or partially ionized. Okay, so what do we mean by that? Well, let's take an example of a weak acid such as ethanoic acid, and any carboxylic acid for that matter. So ethanoic acid is, of course, CH3, COOH, okay? And if you were to dissolve this in water, so you would, what you would find is that an equilibrium is established between your ethanoic acid and ethanoate ions, so CH3, COO minus, and AQ, aqueous, and H plus ions. Okay, so the difference between the strong acid and the weak acid is the fact that for your weak acid, you will get partial ionization or partial dissociation, and only a small proportion of your weak acid actually breaks up to give you your H plus ions and the anion associated with that weak acid. So if we highlight this in yellow, and perhaps the reversible arrows here are key, so unlike strong acids where you get complete dissociation, with your weak acid, you've got partial dissociation. And it's worth noting that most of our ethanoic acid is undissociated. Okay, so that is the difference between a strong acid and a weak acid. The final bit of theory that we want to discuss at this stage is what a neutralisation reaction is. And simply put, it's the coming together of an H plus ion and an OH minus ion in equal amounts so that we form water, and there are no H plus or OH minus ions left in solution. Okay, so we can write this as an ionic equation. So we've got an H plus aqueous ion reacting with an OH minus aqueous. And this results in the formation of water. So at the heart of any neutralization reaction involving an acid and an alkali is the formation of water. Okay, so H plus ions neutralized by OH minus ions to give you a water molecule. Okay, so at this stage, it might be worth looking at an actual exam question to see, to check our understanding of some of the theory we've just been looking at. And you should be able to see if I can bring this up for you. If I stop sharing for 1 second, let's stop sharing my screen. Hopefully you can still see me. And if we look at our chat box, we should find that there is an exam paper, which is your June 2016 paper 1, so breath in chemistry. And we're going to be looking at, I believe this is question 4. Okay, so I will share my screen once more so that you can see the question from this paper. So June 2016, breath in chemistry, which I have shared with you in the chat box. And if you bear with me 1 second, I'll bring up my iPad screen again. Okay, so we've got a question here from our 2016 paper, and we're asked to say which equation is not a neutralization reaction. So the first equation is calcium reacting with hydrochloric acid. Second reaction is H plus reacting with OH minus ions. In the third reaction, we've got potassium carbonate and nitric acid reacting with, so potassium carbonate reacting with nitric acid. And in the final option, you've got ammonia reacting with hydrochloric acid. Now, if we consider the definition we gave earlier of neutralization reactions, hopefully you should work out and be able to rule out that if we highlight B, so we can rule out that as being a neutralization reaction. Okay, we make a little note next to it. So that's what a neutralization reaction is. And then if we consider C as well, we can see that potassium carbonate is a base and it is reacting with an acid in the form of nitric acid. And so again, we can rule that out because it is a neutralization reaction. And finally, we've got ammonia in D. We've got ammonia, which we did identify earlier as being an alkali, and it's reacting with HCl, aqueous. So again, we can rule that out as being a neutralization reaction. And so the correct answer, we're left with A, which shows a metal reacting with hydrochloric acid. Okay, so if we highlight or circle A and write our answer in the box. Okay, now it is important at this stage to point out that students often mistake metal acid reactions such as the one shown here as being neutralization reactions. What in fact is going on is a redox reaction. Now you may not have done redox chemistry yet, certainly you will be doing that very soon. And you should be able to work out, if we wrote half equations for A, that you're starting off with the element calcium, which has atoms with no charge on them. And in the product calcium chloride, you're forming Ca2 plus ions. So CaCl2 has got Ca2 plus ions. So the calcium has actually lost electrons to form Ca2 plus, and therefore has been oxidized. And if you pay attention to the H plus ions in your hydrochloric acid, they gain electrons when they form the H2 molecule. So A is actually a redox reaction. Okay, so something that you will be doing later on this year if you haven't done so already. So we can very sort of quickly rule A out as not being a neutralization reaction. Okay, good. So hopefully the definition of acids and alkalis and the definition of neutralization is very clear. But certainly, if it isn't, do leave a message in the chat box, and I'll be more than happy to get you an answer. Okay, so that sort of ends the first sort of part of this session on acids and titration calculations. Before we do the titration calculations I spoke about earlier, I'd like to spend the middle section looking at sort of practical, the practical side of acid-base chemistry and the titrations that you will be carrying out as part of your assessed practical regime. Okay, so there is a very important, I'll stop sharing for a second. Bear with me 1 second. Okay, so there is a very important resource that I will be sharing with you shortly, and this this resource is the RSC's Interactive Lab Primer. I will highly recommend this resource to anyone doing A-level chemistry. It goes through a number of practical techniques, and it goes through in quite a lot of detail how to sort of improve on your sort of practical chemistry skills. And this is, of course, invaluable for the assessed practical work that you're doing. Okay, so I'll show you the Interactive Lab Primer shortly, and this requires me to share the screen with you. So I will. Very good. So you should have the Interactive Lab Primer on titrations on your screen at the minute. And to access this page, you simply need to Google RSC or the Royal Society of Chemistry and Interactive Lab Primer. And this takes you through a number of practical techniques that are encountered at A-level. Of course, the relevant practical techniques we're looking at today are titrations, but also forming or making a standard solution to use in a titration. And indeed, what I'll do is start off with the page on standard solutions. So again, we're still with the RSC's Interactive Lab Primer, and it may be that you need to register to gain full access for all of the different resources they've got, but this is free and it only takes about a minute to sort of give them sort of the minimum of details, sign in using your school's email address, and everything on the site is free. So we're on the Interactive Lab Primer looking at standard solutions, which of course you will or can use in titrations. As you can see there is a video showing how a standard solution is prepared. And then you've got a number of other resources as well. So you've got the apparatus guide for carrying out for making a standard solution. So you've got weighing bottles, naming apparatus is important. You will, on your A-level exam, sometimes be required to draw diagrams and sort of correctly label apparatus, so making sure you're familiar with all the names. This is a distilled water wash bottle, which you will be using in titrations and making standard solutions, rinsing so pieces of glassware, making sure all of your solid is dissolved. Beakers and stirring rods. You've got the volumetric flask, very important for measuring an accurate volume of a solution, just one fixed volume. There are different sizes of volumetric flask, so typically a 250 centimeter cube volumetric flask, but you can get smaller sizes as well. And of course, funnels for adding solutions, transferring solutions from one vessel into another. Okay, so that's your apparatus guide. There is a handy sort of calculator here for working out sort of masses needed for particular concentrations. So, for instance, you can type in here 150, or sorry, so we've got 1 point. Yeah, so we're saying a 1.0 mole concentration, and you've got here a volume in decimeters cubed of, let's say, 0.5. Let's go for 0.5 decimeters cubed. And if we press the go button, it tells you how many moles are required, and you can also then from that work out what mass by putting in the MR of the solid in question. Okay, so we've got 0.5 moles, and the MR, if we arbitrarily choose an MR of, let's say, 150, and press we should then be able to see the mass calculated for us. So a very large mass, but of course, understandable given that we've arbitrarily chosen sort of numbers to use in this calculator. Okay, so you can use that calculator, and of course, you've got a standard solution concentration calculator shown here. So what we were doing earlier was a mass calculator. Okay, so all of this is very useful for making a standard solution. Of course, a standard solution is one whose concentration is known very accurately. And to make the standard solution, you'll often need a solid that is very soluble in water, that has a very large MR, because this makes weighing it sort of more accurate. You reduce the inaccuracies in weighing. And so this, your solid must also be quite resistant to decomposing. It must be a robust solid for using in your standard solution. Okay, so if we then look at the page on carrying out titrations, so there's the interactive lab primer titration page, and there is a handy, I just want to very quickly show you a very handy guide to titration apparatus. Just as with the standard solution page, you've got a titration video, which we've just scrolled onto. I shan't play it. And then you can also look at the apparatus guide. So on your screen at the minute, you should see very shortly all of the apparatus required. So you've got a wash bottle, you've got a pipette and pipette filler, and then if you move along one, you've got your volumetric flask and a white tile, often used to allow you to visualize the endpoint more accurately. And then you've got a burette, and in the case of dark solutions, you can have burettes that have sort of white markings on them to allow you to read volume accurately. And then you should always have a funnel to add your solutions into your burette. So any standard solution that you make is often used to fill the burette, and the unknown solution is pipetted into your conical flask. Okay, so that's a handy guide to the pieces of apparatus you will need. We can then look at a simulation of a titration. So here is a titration animation for you to have a look at. And so you've got the unknown shown in blue, and you've got the standard solution which you've prepared in your volumetric flask. And if we press play on the simulation, you should find that the unknown is pipetted and transferred into your conical flask. And typically you would be pipetting a fixed volume of 25 centimeters cubed, sometimes smaller volumes using a 10 centimeter cube pipette. And then you can see that your standard solution in red is found in the burette. And if we press start, if we skip this bit, there we go. So if we press start, we can see the burette being opened up and the standard solution added to the contents of your conical flask. And this should, of course, neutralize the contents of your conical flask. And you will see a color change due to an appropriately chosen indicator being added to your to the contents of your conical flask, so that at the end point of the precise volume at which your indicator pH, precise pH at which your indicator changes color, you do know that your substance has been neutralized. Okay, so that is, in short, a very sort of quick and hopefully you'll find very useful guide to how to use your titration apparatus. Of course, in your own time, I will suggest that you download the video or simply stream the video so that you sort of get to grips with sort of the intricacies of carrying out a titration. Again, if you have questions on titrations and how to ensure that your titrations are accurately carried out, do drop me a line in the chat window, and I'm more than happy to answer any technical questions for you. Okay, so that leaves us with a bit of time to tackle some actual titration calculations. And again, I will select one from the same exam paper that I've shared with you. So the June 2016 AS paper 1, so breath and chemistry, and it's question 22 part C. Okay, so I will share that on the screen very shortly. But if you are logged in and signed in and watching this live, if you have a look at question 22 part C, and if you just give me 1 second, I will share this question on the screen with you. Okay, so we do have a question paper on the screen at the minute, and what we'll do is we scroll through to question 22, and we're looking at 22 part C. I'm going to talk you through sort of the essential skills, making sure that you you can do these questions confidently and sort of without losing much time, and certainly without losing any marks at all. Okay, so on your screen at the minute, we've got question 22 part C of the June 2016 AS breath in chemistry paper, and I'll read out the question. It says a student prepares a solution of sodium sulfate Na2SO4 by adding 6.25 times 10 to the minus 2 moles per decimeter cubed of sulfuric acid. He does so from a burette to 25 centimeters cubed of 0.124 moles per decimeter cubed sodium hydroxide in a conical flask. And you've got a balanced equation given to you. In any titration calculation where there isn't an equation given to you, you need to make sure that that is the first thing you do, that you write down a balanced equation where possible. Okay, so we're asked to calculate the minimum volume of the sulfuric acid that the student would need to completely react with the NaOH present. Okay, so if we have a go at doing this question, and I will be going through some of the steps that you should be taking to make sure that you get full marks on this. So there are 3 marks altogether. I've just got rid of the yellow highlight. One of the things that students trip up on often is sort of misassigning concentrations and volumes to the wrong substance, so to the wrong formulae. So if we start with a yellow highlight and we look at sulfuric acid, we're told that we're adding 6.25 times 10 to the minus 2 mole per decimeter cubed sulfuric acid. So I'm going to highlight that in yellow, and I'm going to highlight my sulfuric acid in yellow as well. Okay, so I know that the quantity given, the concentration given, is that for sulfuric acid. And in a different color, we're going to go for pink. I'm going to go 25 centimeters cubed of 0.124 mole per decimeter cubed sodium hydroxide. Okay, right. So we are in a position to be able to work out accurately what the number of moles of sodium hydroxide is. Okay, so if we look at our equation, and I will write this equation out again. So you've got 2 moles of NaOH, and we've got H2SO4, and we're forming Na2SO4, and of course 2 moles of water. Now, the reason I've written my equation out once again is so that you can see how neatly I set out my calculation, doing all the relevant calculations for a particular compound underneath the formula for that compound. So I've got the equation written out, and I'm going to call that line E, and the next line would be to work out the number of moles. Okay, so moles, and we've got enough information to work out the number of moles of sodium hydroxide. Okay, so we're making sodium sulfate by adding 6.25 times 10 to the minus 2 mole per decimeter cubed sulfuric acid from the burette to 25 centimeters cubed of 0.124 moles per decimeter cubed NaOH. Okay, so if we want to work out the moles of NaOH, we need to think about the formula concentration equals number of moles over volume in dm cubed, and therefore the moles is the volume in dm cubed times the concentration. Okay, so moles is equal to our volume in dm cubed, 25 over 1,000. And if we multiply that by the concentration, so 0.124, and if I take out my trusty calculator and quickly do this at 0.025 times 0.124, we should find that we've got 3.1 times 10 to the minus 3. Okay, so 3.1 times 10 to the minus 3 moles. Okay, so hopefully that is clear enough on your screens. Okay, so that's the first thing to do. So the data we've been given allows us to work out the number of moles of our sodium hydroxide. Now, we can use that and the molar ratio. So I write molar ratio in the next line of calculation. The molar ratio of our sodium hydroxide to sulfuric acid is 2 to 1. Okay, so every 2 moles of sodium hydroxide you've got will react with 1 mole of sulfuric acid. Now, if we therefore take, and it's worth writing down the molar ratio again. So if we have 3.1 times 10 to the minus 3 moles of sodium hydroxide, it should react completely with half that number of moles of sulfuric acid. Okay, so we can work out the moles of sulfuric acid, which would be 3.1 times 10 to the minus 3 divided by 2, and that should give us 1.55 times 10 to the minus 3. Okay, so we've got 1.55 times 10 to the minus 3 moles of sulfuric acid. Okay, so we've got the number of moles of sulfuric acid, and we know what the concentration of sulfuric acid is. So we are in a position to work out what the volume is. Okay, so the final step, and here I will sort of make a bit of room on the right-hand side to work out the final answer. Okay, so we know that concentration is equal to number of moles over volume in dm cubed. So our volume in dm cubed should be equal to the number of moles divided by the concentration. And therefore we've got 1.55 times 10 to the minus 3. And we're going to be dividing that by the concentration of sodium, sulfuric acid, which is 6.25 times 10 to the minus 2. Okay, so we're in position to get our final answer. So we divide 1.55 times 10 to the minus 3 by 6.25 times 10 to the minus 2. If we times 10 to the minus 2, there we go. And we should have an answer of 0.0248. So all of our data is given to 3 significant figures. So our final answer to 3 significant figures would be 0.0248 decimeters cubed. We do want our answer in, apologies, we do want our answer in centimeters cubed, so that should be 24.8 centimeters cubed. Okay, so 24.8 centimeters cubed. Okay, so that is our final answer. What I'll do next is to put up another calculation for us to have a go at. And if I stop sharing for a second and go back to my full screen. Okay, so here we go. So, right, so to go over this calculation, we've got an equation written down, and what we've done is calculated the number of moles required, or rather the number of moles for one of our reagents. We've got the concentration and we've got the volume for that particular reagent, so we've worked out the number of moles for it. And we've used the molar ratio to allow us to work out the number of moles of sulfuric acid that would be reacting with your sodium hydroxide. And then, knowing the concentration of our sulfuric acid, we've used that concentration and the calculated number of moles to work out a volume in, first of all, decimeters cubed, and then converting it into centimeters cubed. Okay, so that is a fairly standard calculation you will see at A level, and it requires you to be very confident on sort of mole calculations and so learning all the different formulae you need to work out the number of moles. So in this instance, we've got solutions, and so knowing the relationship between concentration, number of moles, and volume. In some instances, you will be required to think about the relationship between masses and the relative formula masses of compounds. And of course, if you're working with gas, you'll be looking at the molar-gas relationship, or in some instances, using the ideal gas equation. So these are all the different ways of calculating the number of moles. And invariably, sort of your any calculation sort of you do requires you to deal with molar quantities. So you need to make sure that you've brushed up on all of your mole calculation skills. Okay, so there is, I've got some more questions for us to have a go at, and what I'll do is present the next question for you. I will share my screen to allow us to do that, so if you bear with me for 1 second. Brilliant, so I've got a sheet here which shows some calculations, and quite a lot of these calculations are completely unstructured, so you do need to be able to figure out a path to the answer all by yourself. And so what we want to do is highlight the pieces of information given and match them to the correct formula in our equation. And then what we want to do then is work out the number of moles of whatever substance we can work out the number of moles for, and use the equation, use the molar ratio to allow us to work out the number of moles of the unknown, and therefore access the final answer. Okay, so we're going to look at, let's choose question 2, which is fairly similar to the example we've just worked out. And then, well, let's very quickly, let's check. Let's look at, yes, so we will look at question 2. And what I'll do is I'll share my iPad screen with you. So I'm going to change screens for a second. I have got question 2 cut out and pasted onto this blank screen. And in this question, again, we're being asked to calculate the volume of 0.1 mole per decimeter cubed hydrochloric acid that would neutralize 25 centimeters cubed of 0.16 mole per decimeter cubed sodium hydroxide. And so if we look at the equation and write it out again so that it spans the width of our page. So you've got HCl plus NaOH going to NaCl and H2O. And then, as I said, highlighting the information given. So you've got 0.1 mole per decimeter cubed hydrochloric acid. So that's in pink. And if I choose a different color, yellow, for our sodium hydroxide, we've got 25 centimeters cubed of 0.16 mole per decimeter cubed sodium hydroxide. Okay, so we should immediately be able to see that we've got enough information to work out the moles of sodium hydroxide. Okay, so if I do that, the number of moles of sodium hydroxide is equal to the volume, which is 25 over 1,000. So the volume in decimeters cubed times the concentration, which is 0.160. Okay, and that gives us, okay, we've got 0.025 times 0.16, and that is equal to 4 times 10 to the minus 3. Okay, so we've got 4 times 10 to the minus 3 moles of sodium hydroxide. And then the next thing we need to do is to look at the molar ratio of hydrochloric acid to sodium hydroxide. So I use a different color, perhaps that there, to look at the two substances we're considering here. The molar ratio is 1 to 1. So 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide. And that therefore allows us to work out that we should have 4 times 10 to the minus 3 moles of hydrochloric acid. Okay, so having worked out the number of moles of hydrochloric acid, we do know the concentration of hydrochloric acid. It is given to us in the question as 0.1 times 0.1 mole per decimeter cubed. Okay, so the final answer requires us to work out a volume. It doesn't specify what units for volume, so we will leave it in decimeters cubed. Okay, so we've got volume being equal to number of moles over the concentration. Okay, and so we've got 4 times 10 to the minus 3 divided by the concentration, which we're told is 0.1. Okay, so that should give us a volume of 1. That should be 0.04, so 0.04 decimeters cubed. Okay, and so a very similar question to the last one, straightforward, although unstructured. And if we label the different steps we've carried out, if I do this in red, so we've got the equation here, and then we've got the number of moles, which is the first calculation we do. And then in the third step, we're using the molar ratio, which we obtain from the balanced equation. And then finally, our answer, which in this case is the volume required of our hydrochloric acid. And if I highlight the first letters of each of these steps, you see that it spells out EMMA. So that's a handy reminder as to the steps you need to take to get to the final answer for any of these titration calculations that we look at. Okay, so we've got about 7 or so minutes to consider the very last question, which is by far the trickiest. So if we look at this question, which I've got on the screen, a much harder, much wordier, sort of unstructured question where you've got 2.960 grams of a monoprotic acid. So this is an acid, a bit like HCl, it only donates 1 proton per mole of the acid. So 1 mole of the acid reacts with 1 mole of OH minus ions. It's dissolved in water and the solution made up to 250 centimeters cubed. 25 centimeters cubed portions of this solution are titrated against 0.2 mole per decimeter cubed sodium hydroxide solution, requiring 20 centimeters cubed for neutralisation. And we're required here to calculate the MR of the acid. Okay, so let's put into motion sort of the tips I've just given you about highlighting information. Okay, so we've got our highlighter, and we know that we've got 2.96 of our monoprotic acid, 2.96 grams of the monoprotic acid was dissolved in water, and the solution made up to 250. Okay, so 250 centimeters cubed. And then we take 25 centimeters cubed portions of this solution. So everything in yellow belongs to the monoprotic acid. And this is titrated against sodium hydroxide of concentration 0.2 mole per decimeter cubed. So I'm going to go 0.2 mole per decimeter cubed of sodium hydroxide in pink, and 20 centimeters cubed of our sodium hydroxide is required for neutralisation. Okay, so there we go. So all of my sodium hydroxide is in pink. Now, we need to write out an equation. Yes, we don't know the formula of this acid, but we can, because it's a monoprotic acid, use the HX as a generic formula for it. So imagine Cl being X, so it'd be HCl. Okay, so HX is our generic monoprotic acid, and this is reacting with sodium hydroxide, and this should form NaX and some water. Okay, so that is our balance equation. Now, before we do any calculations, let's look at my diagrams showing what has been, what all of those words in the question mean in terms of the actual experiment being carried out. So I'm going to go back to my highlighter again, and I'm going to highlight everything in yellow this time. So you've got your HX, which is your monoprotic acid, and we know that 2.96 grams of it is dissolved in 250 centimeters cubed, and that's what you've got in this volumetric flask. And then you're taking 25 centimeters cubed of the solution you've just made, and you're pipetting it into a conical flask. Okay, so pipette 25 centimeters cubed into a conical flask, and then you're titrating it against sodium hydroxide. Okay, so you've got sodium hydroxide in your burette, and it has a concentration of 0.2 moles per decimeter cubed, and we're told that our titer is 20 centimeters cubed. Okay, so that's my question sort of turned into a series of simple diagrams to allow us to actually follow through on the steps being carried out in this neutralisation. Okay, so to complete my highlighting, I've got my HX in the conical flask shown in yellow again. Okay, so the first thing we can do is work out the number of moles. Do we have enough information to work out the number of moles of one of our reactants? The answer is yes. We've got 0.2 moles per decimeter cubed of sodium hydroxide, and we know the volume of it. Okay, so we can work out the number of moles, which would be the concentration times the volume in decimeters cubed. So concentration is 0.2, and we've got a volume of 20 centimeters cubed, which is 0.02. Okay, so 0.2 times 0.02 gives us 4 times 10 to the minus 3 moles. So 4 times 10 to the minus 3 moles of our sodium hydroxide. Okay, so if that's how many moles of sodium hydroxide coming out of our burette to neutralize our 25 centimeters cubed of HX, the question is, how many moles of HX have we just neutralized? And that is fairly straightforward. We simply need to consider the molar ratio. So if we use our EMMA acronym again, and moles, we need to consider the molar ratio. And that, of course, is 1 to 1. And therefore, we've got 4 times 10 to the minus 3 moles of HX in 25 centimeters cubed. Okay, so 25 centimeters cubed of HX has got 4 times 10 to the minus 3 moles. Now, we're working backwards, right? We need to work out the MR of HX. So if we work backwards, if we know how many moles of HX is in 25, moles of HX in 250 is simply 4 times 10 to the minus 3 times 10. Okay, that should be 4 times 10 to the minus 2 moles. Okay, and then finally, to calculate the MR, we know that number of moles is equal to mass over MR, and therefore our MR is going to be equal to the mass over the number of moles. Now, we worked out, or rather we were told what the mass was at the very beginning in the question, highlighted in yellow, 2.960 grams, and this is divided by 4 times 10 to the minus 2. Okay, so 4 times 10 to the minus 2 divided by, sorry, I've got things the wrong way around, 2.960 divided by 4 times 10 to the minus 2, and this should give us 74 as our MR. Okay, and if you're wondering what monoprotic acid gives you or has an MR of 74, I worked this out earlier to be propanoic acid. Okay, so propanoic acid is a carboxylic acid. It's an organic acid. So that is our final answer. Okay, so hopefully you should be able to go away and tackle some of the questions you've got. Tackle some of the questions you've got on that sheet. And again, if you have any trouble at all doing these, you can always get in touch with either myself, Dr. Owusu, or Miss Batten, or certainly your teachers at school, Miss Lee and others, to talk you through and work you through these calculations. That brings us to the end of this session on acids and alkalis and titration calculations. Hopefully the examples we've worked through are enough to to go away and do the rest of the questions on the sheet independently, and also to tackle some more practice problems in exam papers of the type we saw in that paper one from 2016. I hope you've enjoyed this session, and I look forward to seeing you again next Sunday on our next live chemistry clinic. Thank you very much for joining me.